Welcome to PH4410 Econophysics. In the previous video segment, we have shown how we can take the historical prices downloaded from Yahoo Finance, for example, for the company Apple, convert those price time series into a return time series, and then plot the histogram of the returns. So for Apple in particular, we saw that the returns is actually narrowly distributed between minus 0.2 and 0.2, and in particular it is non-zero, strictly within minus 0.15 and 0.15. Now this particular distribution looks fairly similar to a Gaussian distribution, but in order to make a quantitative comparison, we need to plot this histogram against the normalized Gaussian distribution to make a quantitative comparison. Now, in order to do that, first we have to be able to plot this graph in a semi-log plot, and the easiest way to do it is to create our own bins. For example, let's say we create our bin centers from minus 0.15 in steps of 0.01 to 0.15. And then we will end up with 31 bins centered at from minus 0.15, minus 0.14, all the way to 0.15. Now, these bins have edges. Let's say the bin that is centered at minus 0.15. If we want the interval, if we want the bin size to be 0.01, we would need the bin edges, the edges of this particular bin, to be at minus 0.155 and at minus 0.145. So we can create these bin edges by doing this 0.155 in steps of 0.01 until we reach 0.155. And then we find that we have 32 bin edges that are covering the 31 bin centers. Now, how would we accumulate the frequencies for the individual bins? What we can do is we can write down a for loop for b equals to 1 to 31 because they are altogether 31 bin centers. And then fb of b, the frequency in bin b, would then be equals to the sum of two parts. First, r must be greater than the lower bin edge. So this is bin b. Okay. Now at the same time, it must be less than or equals to the upper bin edge, which is bin b plus 1. Okay, so if we do this, we plot n, and then we can then just bar this bin center fb, and we will find the same distribution between minus 0.15 and 0.15. Now, because we have used a symmetric bins between minus 0.15 and 0.15. This looks, even closer to a normal distribution. But is it really a normal distribution? We can check by changing the y scale to a logarithmic scale. This is done with the function set GCA, which is the current current axis, and then we will set the y scale to log, and then we can see that, okay, and now what is happening here is that the Octave does not like to convert a bar graph into semi-log scale, so you see it's giving problems. So what we can do is we can do a stairs instead. So we can do stairs FB. So this will look like a merged version of the histogram, the bar histogram. And then what we can next do, is, let's see whether this is at the correct place. Now this is not good because this is right stairs. So what we should do is use the bin edges from 1 to 31. Now it is good. So this is where the bin center is exactly at 0. So now if we do set GCA Y scale, then you see that it is really plotting the x scale in a linear scale, x axis in a linear scale, and y axis in a logarithmic scale. Now you can see that this thing doesn't look like a quadratic curve, which is what we expect from a normal distribution. But in order to do the comparison more properly, we first have to normalize the distribution. So first, let's say FB is we divide FB by the sum of FB, and next we divide by the width of the bin, which is 0.01. So if we do this and then we stairs again, so if we stairs again and set the Y scale again, now we can see that we have the distribution, the empirical probability distribution goes slightly above 10 and then falls off all the way to about 10 to the minus 2. Okay, now we're ready to superimpose on this we're ready to superimpose onto this histogram the normal distribution that is consistent with the mean and the average that is obtained within this interval. So first of all, we have in the original returns array, we have returns not only between minus 0.15 to 0.15, but we also have returns that are beyond that. So what we can do is we can select only those that are between these two limits. So what we can then do is, let's say we k equals to find r greater than minus 0.155. So that is the lower band edge of the lower bin edge of the lowest bin, and then then we say r1 is equals to rk. Okay, this will give us only returns that are above minus 0.155. But of course, we still also want to cut off the top end. So we go for less than 0.155 because it's up. This is the upper band, upper bin edge of the uppermost bin, and then we can do R2 equals to R1k, and if you look at R2, then the R2 will be only strictly between minus 0.155 and 0.155. Okay, so the mean of R2, this array which is does not include any returns that are below minus 0.155 and any returns that are above 0.155, the average is 0.001189, and the variance of this particular restrictive array is 7.77 times 10 to the minus 4. Now we're ready to plot the normal distribution that has the same mean and variance. So let's say that we call that new variable ff equals to exponential minus, so bin center minus, what else do we have? Minus we have bin center minus, actually we don't need bin center, we can have bin h minus as well. So minus the mean of R2, raised to the power of 2 divided by 2 times the variance of R2. This is inside the exponential, and then divided by square root of 2 times pi times the variance of R2. And so we hold the figure, and then we plot bin ff and make it red, and you can see that the axis, we need to do something about it. So again, we go, the axis will go from minus 0.2 to 0.2, and then we want to go from 1 e minus 2 to 1 e2. And you can see that this is compared against the theoretical normal distribution. The empirical distribution is a little bit more sharply peaked than the normal distribution, and more importantly, you find that at intermediate values of returns, whether it's positive or negative, the empirical curve, the empirical histogram falls below the theoretical normal, whereas at larger values of returns, both positive and negative, you see that it develops a fat tails and rises above the probability distribution expected from the normal distribution. Okay, so this is why we say that in the real market, the return distribution is not really a normal distribution unless you have returns that are defined on very long time horizons, like 1 week, 1 month, 3 months, half a year to a year. Whereas for higher frequency, typically 1 day or below, we find that the empirical returns distribution tends to deviate quite a bit from the normal distribution. Most important feature, besides the sharper peak at close to zero returns, it's also the fat tails, both at the positive and the negatively large returns.